Cool. Welcome, everyone. It is great to see you all. It is my distinct pleasure to introduce Patricia Klein, University of Minnesota, who will tell us about bumpless pipe dreams encode Gröbner geometry of Schubert polynomials. Patricia.
Thank you, Carrie, for the introduction, and thank you, Carrie and Eloisa, for the invitation. It's very nice to be here. I want to start with a brief description of what is Schubert calculus. So what is the type of thing that I want to use commutative algebra to study? So a classical problem is, suppose you have 4 lines in complex 3 space, and they're in general position. How many lines meet all 4 of those lines? This image is from Frank Sotil's website. It's a lovely image. I am grateful to him for posting it so that we and all the world can use it. So we're going to picture, for example, these 4 blue lines, and then we ask, how many lines can we draw in like M1 and M2 that meet all 4 of these? And as we try to formalize this and move towards Schubert calculus, this then morphs. So given, I'm going to change this display, sorry. Yeah. Given 4 planes through the origin in complex projective 4 space, how many planes through the origin meet all 4 of those planes, not counting the origin? So this is a way of capturing the general position in a very manageable way. We love projective space. Okay, so now our first appearance of Schubert. This problem can also be phrased as what is the intersection of 4 Schubert varieties in the Grassmannian G2-4. So we've taken our very concrete question about lines and planes, and we find that it's equivalent to asking about some intersection of some varieties in the Grassmannian. So this particular problem, because it's about projective planes and 4 space, lives in G2-4, but plenty of these other enumerative questions live elsewhere. So something that captures a lot of them is the complete flag variety. So we can lift these varieties that we'd like to intersect back up to the complete flag variety. So what is that? That's where questions like this live. So a flag is a chain of vector spaces, and I'm chaining up to n-dimensional space, and I have n vector spaces, and they're strict containment, so we better increase in dimension 1 each time. Equivalently, the dimension of each vi is I. And so, for example, we could think of this by taking our favorite invertible matrix and considering the successive span. So span of the first column, span of the first 2 columns, span of the first 3 columns, and we're getting a nesting like this. My favorite invertible matrix is the identity matrix. So now let's think about the identity matrix. And thinking about the identity matrix, it's not so hard to see that the upper triangular matrices stabilize the flag that's given by the identity matrix by taking span of the first column, span of the second, and so on. So we have the general linear group, and it's acting transitively on this space of flags. So using just essentially the orbit stabilizer theorem, we can pick our favorite flag. So for me, it's the one given by the identity matrix, and see that the stabilizer is upper triangular matrices. And so we can realize this set of complete flags as the group that's acting mod the stabilizer. So identifying the complete flag with GLN mod U, we can now endow this set of complete flags with some geometry and with a topology. And so I'm just taking the usual topology on GLN and quotienting by this subspace. We now have a topological space, and it makes sense to ask about things like holes in it. So we can do cohomology. Okay, so as you may recall from linear algebra class, there are LU compositions of a lot of matrices. So most invertible matrices we'll be able to write as just a product of some lower triangular matrices and then a product of some upper triangular matrices. Occasionally, we have some of those northwest minors that vanish, and so we really have to force ourselves to change the positions of some rows, and so that's where our permutation matrix is coming in. So either we just write our matrix as product of lower triangular times product of upper triangular, or we stick a permutation matrix in the middle so that we've rearranged the rows of our invertible matrix so that then we can do this decomposition. This gives us an equivalence relation. It decomposes, that's not true. This decomposes GLNC into these cells, and they're called Bruja cells. So by cell, we really mean sort of cell in the topological sense, where a Bruja cell is homeomorphic to a copy of affine space. And so we can glue together these Bruja cells to give us the flag variety. So fix your very favorite permutation matrix and then consider LWU for that permutation matrix. So this is something that's in GLN, and we saw that we had a surjection from GLN to the complete flag variety. And so by mapping down, we can take this Bruja cell and get a Schubert cell, and the Schubert cells live in the flag variety. We like varieties, which means we like closed things, so we take the closure and we get a Schubert variety. Okay, so this has been a lot of, I guess, topology and a little bit of linear algebra. Why, as commutative algebraists, do we care? Well, one answer is because we really like the Cohen Macaulay property. And historically, we at least care because Schubert varieties gave us some of the first examples of Cohen Macaulay varieties. So these were really, growing up in the 70s and 80s. And obviously we need examples to understand the math that's going on. And Schubert varieties, through just sort of this list of works that's cited here, and actually many others, gave us some examples of the Cohen Macaulayness and helped the emergence of that area of commutative algebra. So historically, commutative algebraists like Schubert varieties because we like the Cohen Macaulay property. But maybe you say, great, we understood. It was really nice that those Schubert varieties got us started. Now we have plenty of other examples of Cohen Macaulay rings, Cohen Macaulay varieties, Cohen Macaulay modules. And, maybe it's like Citizen Kane, where people who like the history, really like how that camera went through the roof. But now you've seen a lot of cameras go through roofs, and do you really need that anymore? So they're still relevant to us, I claim. And so we one way that we can get back to commutative algebra that we take on faith is modern, is that there's this really great commutative ring with unity that's fun to study. And that commutative ring with unity that's really fun to study is a polynomial ring over the integers, mod the non-constant elementary symmetric polynomials. So the non-constant elementary symmetric polynomials are the sum of all of the xi, or the sum of all of the products of 2 of the xi, or the sum of the product of all of 3 of them. So to get a symmetric polynomial, you should be able to re-index the xi and get the same polynomial on the nodes. And the elementary symmetric ones look like this sum of all possible products of a certain degree. Okay, so this ring, how does it connect back to what we've been talking about? Well, Borel showed that this ring is the cohomology ring with coefficients in the integers of the complete flag variety. So if you do like those enumerative questions, if you do like thinking about the intersection of Schubert varieties, then you like this cohomology ring as a cohomology ring. Or if you don't really care so much about those intersections and about the topology, then maybe you just care that this is a great commutative ring with unity. So what's one thing that's really great about this commutative ring with unity? Well, it has some good coset representatives. So the coset representatives that are, I think now favored, is fair to say, are the Schubert polynomials. So Schubert polynomials are valuable combinatorially because there are a lot of different formulas for them. And one reason why I like them is if you take two Schubert polynomials and you multiply them, then they expand as a sum of non-negative integer multiples of other Schubert varieties. So you don't really have to think about this quotient at all. You take your coset representatives, you multiply them, you express them as a z-linear combination of your other coset representatives. So having a quotient ring that you don't have to think of as a quotient ring, I think was always a virtue. So let's go and Knutson and Berger also introduced the double Schubert polynomials, which are refinements of single Schubert polynomials. And they also come about naturally for topological geometric reasons. So they represent torus equivariant cohomology, and they actually are, so the T by T, if you take both of the Borels, U and L, so if you have this torus cross torus action, then your cohomology ring is literally a polynomial ring, and the double Schubert polynomials are the elements of that ring that correspond to your Schubert varieties. So these Schubert polynomials and double Schubert polynomials are topologically desirable, and they're combinatorially desirable. But you may wonder, do they have algebrogeometric value? And one answer to that question comes from Fulton's matrix Schubert varieties. So now we're going to get to an affine variety that is a generalization of a determinantal variety. So this I hope again feels like home to a lot of us. So I'm going to define matrix Schubert varieties just by example. So fix your favorite permutation in Sn, not necessarily your favorite. I don't know whose favorite is this one, but we'll consider this one. And here's how we define the matrix Schubert variety that corresponds to it. So first we write down our permutation matrix, and my conventions for the permutation matrix are that this 4 is telling me that in the first row, I put a dot in the fourth spot. This 7 is telling me that in the second row, I put a dot in the 7th column. And this 2 is telling me that in the third row, I put a dot in the second column. Sometimes, for example, in Artin, the convention is transpose. It doesn't really matter. So having put down, oops, this box is, there you go. So having put down those dots, we then shoot out what are called death rays. And the death rays go down and to the right from each of the dots. So everything in blue here is a death ray. And what's left over are these boxes with numbers in them. They come to us without numbers in them. And we can then give a rank matrix. It's a rank matrix in two different but related ways. So one way is that the number that I put in the blank squares is the rank of the northwest submatrix of my permutation matrix at that spot. So for example, here, this 0 is saying that the rank of this permutation matrix in that corner is 0 because it's just a 0. And over here, for example, the rank of this northwest submatrix here is 1 because there's 1, 1 there. So this is equivalent to counting the dots. So look northwest and count the dots. So if I start here and I look northwest, I get 1 dot. If I start here and I look northwest, I get these 1, 2, 3 dots. And that's how these numbers have been put in the boxes. So having written down these boxes, the other way that it's a rank matrix is that it tells us how to define an ideal from a generic matrix, so a matrix full of variables. So if I take a matrix full of variables and I insist on the rank conditions that are in this grid, then I say, well, in this spot, I need an equation that tells me that I'm rank 0 here. So how do I take a generic matrix and impose a relation that makes this 1-by-1 submatrix rank 0? Well, x11 had better be 0. Similarly, x21 better be 0, x31 better be 0, and so on. And over here, all of these 2-by-2 minors in this little rectangle here, well, they also have to be, sorry, I have to take the 2-by-2 minors because I have to be rank 1. And rank 1 means my 2-by-2 minors vanish. So similarly here, and then looking, say, northwest of this 3 here, I'm allowed to be rank 3. So I take the 4-by-4 minors and I throw that in my ideal. So from these rank conditions, I generate an ideal in a polynomial ring. The generators that I've described using these boxes here, these are called the Fulton generators. The Fulton generators say that if I look northwest of these gray boxes, these are what are called the essential boxes. And I say that I'm 0 northwest of here, 0 northwest of there, rank 1 northwest of there, rank 3 northwest of there, rank 2 northwest of there. That's all of the information. So one thing that is worth pointing out is that if I didn't have these 2 gray boxes at the zeros, if all of my gray boxes made a little scoopy arc, then I get what's called a one-sided ladder determinantal ideal. So Schubert determinantal ideals generalize one-sided ladder determinantal ideals. Are there any questions here before I move on? I should say I can't see the chat if there's anything there.
There's nothing in the chat.
Thanks. Okay, so we have our matrix Schubert varieties, and we want to see how these help us understand that double Schubert polynomials are algebra geometrically natural. And that came from Knutson and Miller's work, which showed that there are these combinatorial objects called pipe dreams. And so if we take our permutation W, then the double Schubert polynomial corresponds to the matrix Schubert variety of XW by Gröbner degeneration. So we take our pipe dreams and we read off the crossing tiles to get our Schubert polynomial. So here we have 1, 1 and 3, 1. That gives us 1, 1, 3, 1. Here we have 1, 1 and 2, 2. And that's 1, 1, 2, 2, and so on. And to see how this is coming from the Gröbner geometry, here is for the permutation 2, 1, 4, 3. Here is the Schubert determinantal ideal. If I insist that for every submatrix, the leading term is the product of entries along the off diagonal, the anti-diagonal, then the lead term of this element here has to be x13, x22, x31. And so our prime decomposition of this initial ideal, well, it's always going to have x11 in it, but then we get x31, x22, x13, which we see again as these crossing tiles, x31, x22, and x13. So we have these combinatorial objects that tell us about double Schubert polynomials and also tell us about Gröbner degenerations of these affine varieties we like to study. Okay, but there's a coincidence. And that coincidence is that there are these other squiggles. These other squiggles are called Bumpless pipe dreams. And they were introduced in that name by Lamley and Shimozono in 18. They were previously in the literature due to Lascaux as the 6-vertex ice model. And then Anna Weigandt explained how they were the same. And shored up some of the, Lascaux's not the most careful. I mean, now he's dead, but he wasn't the most careful. So the pipe dreams come about by starting from this thing that looked like the diagram that we wrote out. when we were filling in our rank matrix. So again, it's a first row gets a 2, second row gets an elbow at a 1, third row gets an elbow at a 4, fourth row gets an elbow at a 3. And then we're allowed to do these things called droop moves. So we're allowed to bend an elbow that looks like this into a blank tile like that. And so we're only allowed to droop down, and we're only allowed to droop elbows into blank tiles. There's a couple more rules that aren't so important to us. So the only droops that I'm allowed are drooping this pipe into this blank tile or this other pipe into this blank tile. And so now looking at these 3 bumpless pipe dreams associated again to 2, 1, 4, 3, we read off from the blank tiles the double Schubert polynomial. And it's x11, x33, x11, x21, x11, x12. So I'll remind you of the formula that we had for bumpless pipe dreams for the Schubert polynomial from the pipe dreams. And these are the same polynomial, but they're not the same term by term. You could FOIL this and recollect your terms, and you would get the same polynomial. But the bijection is not obvious. It's not 2 ways of writing down the same polynomial in the same way. And so it's sort of odd that there is this one formula that comes from a classical combinatorial object that tells us how to write down double Schuberts and is canonical from the geometry. And then there's this other formula for double Schuberts that comes from this other combinatorial object. And that's sort of it. And so what we'll talk about for the rest of today is how to see that these bumpless pipe dreams and their formula for the double Schubert also comes from geometry, is also algebra geometrically natural, also has a Gröbner degeneration living in it. So in this case, what we want to do, and maybe before we do this, we should say that, why would Knutson and Miller choose the anti-diagonal? Is it because they aesthetically prefer the anti-diagonal and know on the evidence that Knutson and Miller have good aesthetic judgment? It's because no one likes the anti-diagonal, but those limits are nicer. Those limits are reduced. And so the primary decomposition is prime decomposition. There are no multiplicities to count. So that's the reason for that preference. But a diagonal term order, I love Lex order, just, reading across my my matrix. So diagonal term order is also worth studying. And what happens is these Fulton generators, with respect to a diagonal term order, are not a Gröbner basis. So if we didn't have a 0 here, we had an x11, then we would have that the lead term of x11 is obviously x11, and the lead term along this diagonal would be x11, x22, x33. And so the entire diagonal initial ideal would just be x11, and that's not big enough. So that is not a Gröbner basis. Instead, we have to make a modification in the diagonal setting, where in this case, it's actually enough just to set x11 equal to 0 here. And then with respect to whatever diagonal term order you want, the leading term here is x12, x21, x33. And so here is this initial ideal, which in this case is also radical. And here is its prime decomposition. And now let's read this from the bumpless pipe dreams. So x11, x33, x11, x21, x11, x12. So here we see, at least in this case, the diagonal degeneration lining up with this other formula, this newer formula for double Schuberts. So my theorem with Anna is that if we take any diagonal term order, then the irreducible components of the initial ideal, counted with scheme theoretic multiplicity, naturally correspond to the bumpless pipe dreams of W. This was conjectured by Hamaker, Pechenik, and Weigandt. They showed the result in a special case, which they called Banner, it extended the vexillary case that was due to Knutson and Miller Young in 2019, which is maybe some more evidence that Knutson and Miller also believe that the diagonal term order is worth studying. And again, I'll remind you that vexillary matrix Schubert varieties are also known as one-sided ladder determinantal ideals, and under that name, their Gröbner bases had been studied by, I do not know how to pronounce Claudia Miller's collaborator's last name, but I will try. Gonsulai and Claudia Miller, and then Elisa Gorla. And so on that side, this was also reasonably well studied. Okay, so I want to do an example, and the example that I want to do is actually, instead of just taking one matrix Schubert variety, I'd like to take an intersection of the ideals defining two of them, so a union of the two matrix Schubert varieties. My theorem with Anna does hold in this case, and also this is a small way for us to see how the multiplicity is coming up. So if our first Schubert determinantal ideal is Z11, so this is coming from W1 up here, and W2 is giving us this 2 minor is the unique generator of our second Schubert determinantal ideal. Then in this case, the intersection is actually just the product. So take this 2 minor and multiply it by Z11. And then the initial ideal with respect to any diagonal term order, well, if it's just Z11 times this 2 minor, it better be determined by the main diagonal of this 2 minor. So Z11, Z22. So that tells me that the initial ideal is Z11 squared, Z22. Obviously, this is its primary decomposition. And so what we see is that this ideal has multiplicity 2 at 1, 1, because if I localize at Z11, then I'm getting this length 2. Sorry, I'm going to mod out by the primary ideal, localize at the prime that contains it, so I get something finite length will be over C, so it's algebraically closed. So length is the same as length of the module, the same as vector space dimension. And so this is just dimension 2. And here, when I localize at Z22, then I'm just getting a field. So this is multiplicity 2 here. Looking at the Bumpless pipe dreams, well, here's the Bumpless pipe dream for 2, 1, 3. And clearly there's no drooping that can happen because there's no blank tile south or east of any of these elbows. And when we start with this Bumpless pipe dream for 1, 3, 2, there's exactly one droop move that we can do. It's grouping this elbow into this blank tile. And so in a way that I'll describe in a second, this Bumpless pipe dream for W2 is giving us the same information as this Bumpless pipe dream for W1. So what's happened here is we've taken one of our, we've taken a Bumpless pipe dream for one of our permutations and sort of drooped into the other one. So we're getting a second copy of our Bumpless pipe dream. When we get a second copy of a certain Bumpless pipe dream, or even just with Bumpless pipe dreams with the same set of blank tiles, that's how we get multiplicity in our initial ideal. So the way that this shows up when we start with just one matrix Schubert determinantal ideal is that we end up through an induction drooping so that we get to a situation that looks like this, where we have an intersection of Schubert determinantal ideals. Okay, so the next thing that we want to do is understand these droop moves in terms of some algebra. So we will understand these combinatorial moves that we could sort of see giving us the same blank tiles as Gröbner degeneration. So here again is the set of Bumpless pipe dreams for 2, 1, 4, 3. And here again are these two pipes that we can droop. And what we're going to do is we're going to take X33 to be lexicographically largest. And so this is actually harmless. We can take this lower outside corner, so an essential box that has no essential boxes south or east of it. And because we're taking a diagonal term order, it's fine to say this is the lexicographically largest variable. Ooh, there we go. And so we can do what looks like a vertex decomposition of a simplicial complex. So we can form this ideal C that's going to play the role of the link, and this ideal N that's going to play the role of the deletion. And the way we do that algebraically is we say, look at the generators of my ideal, and everything that involves x33, my strongest variable, take its coefficient, which will just be some other variables, throw them into an ideal, or some other polynomial, I should say. In this case, it's variables. And then take all of the generators that don't involve x33 and put that into a different ideal together with x33. So that's how we're getting this initial ideal, described in terms of a link and a deletion. So this ideal C, the ideal playing the role of the link, it's capturing for us all of the primes that do not contain x33. So C will never ever involve x33. And this ideal here, this n plus x33, well, certainly all of its minimal primes and all of the minimal primes of its Gröbner degenerations contain x33. So we're splitting the set of primes of the initial ideal of IW into two sets, those that contain my strongest variable and those that don't. Here's what that bijection looks like on Bumpless pipe dreams. So we take, one case is that this square stays a square. And so if I'm not allowed to group into the square, then I might as well exchange these two pipes and cancel this box. So by exchanging these two pipes, I cancel this box, and I get another permutation whose Coxeter length is shorter. The other alternative is that I do group into that box. And if I do group into that box, then what I can do is I can take this drooped Bumpless pipe dream and I can sort of just straighten it out. So I'm going to force this wire to go all the way across and this one to go up. And so then what I get is these two other permutations where the lower outside corner, one of the lower outside corners has moved up. It's moved up and west. And so the induction in that case goes by moving the boxes up and west. So again, on the algebra side, we're splitting into the primes that contain my lexicographically strongest variable and those that don't. And in the Bumpless pipe dream side, I'm splitting my Bumpless pipe dreams into those where y is a box and those where y is not a box. So in general, here's how these recurrences go. Fix a lower outside corner y. Y is the name of the variable, but I'm also going to call the box that contains it y. So take it to be lexicographically largest. This ideal in a geometric vertex decomposition that plays the role of a deletion. It is just another Schubert determinantal ideal always. And see this ideal that's playing the role of the link. It's actually what's called an alternating sign matrix variety, and it can be expressed as an intersection of Schubert determinantal ideals. So we take our geometric vertex decomposition and it splits the primes of the initial ideal of I into those that contain y and those that don't. Grouping or canceling the box of y splits the Bumpless pipe dreams of W into the Bumpless pipe dreams of C and the Bumpless pipe dreams of N. And again, this is one Schubert determinantal ideal of smaller length. And this is a bunch of Schubert determinantal ideals with a lower outside corner that's been bumped northwest. So moving towards that corner. At the same time, Lascaux's transition formula, so this is just a purely combinatorial thing. It splits the permutations near W, I won't see what that means, into permutations that correspond to C and those that correspond to N, and those are exactly the ones that we see here. So we recover some underlying combinatorics through the algebra. So what do we want to use this for? As commutative algebraists, we're maybe not satisfied with saying, you know, there are a bunch of combinatorial formulas for double Schubert polynomials, and you know, now we understand those formulas better. I think that's worth doing, but it's not exactly a commutative algebraic result. But what we can use this for commutative algebra comes through some work that I did with generality. And that work says that when we have a geometric vertex decomposition like the one that we just talked about, so it's a geometric vertex decomposition with pretty mild hypotheses that are satisfied here, then we get an elementary G by liaison. So this is something that lives in the linkage literature. And due to Hartshorne, an elementary G by liaison is something that you can use to transfer the Cohen Macaulay property from one subscheme of projective space to another. So when we have this elementary G by liaison, we can start from a matrix Schubert variety. Those are all Cohen Macaulay. And we can find these other intersections of matrix Schubert varieties, these other alternating sign matrix varieties for special kinds of intersections of matrix Schubert varieties. And we can transfer the Cohen Macaulay property from either the union of matrix Schubert varieties or the one matrix Schubert variety we started with to these new ones that we want to study. So there are a few sort of small theorems of this type, and here's one of them, is if we take a bunch of permutations of the same Coxeter length, and we consider the intersection of their corresponding Schubert determinantal ideals, so that's the union of our matrix Schubert varieties, if R mod J and R mod N are both Cohen Macaulay, then actually R mod, this sort of one-step Gröbner degeneration of J, is Cohen Macaulay, and so is C, which is one of the components of this INYJ. So Conca and Barbaro have this lovely result, it's just like my favorite result from the past 5 years or so, which is that if you take any ideal in a polynomial ring and you take a Gröbner degeneration and the initial ideal is square free, then it's actually Cohen Macaulay if and only if the initial variety is Cohen Macaulay. So obviously, usually we get the implication in one direction where if the initial variety is good and the variety you started with was good, but if your initial ideal is square free, it's actually an if and only if. And so I would love to see more results in that direction, where when can we say that maybe you don't get to degenerate all the way, and so you don't but you have some amount of square freeness that's preserved for a step or two. So this is one result that is a small step in that sort of direction, where here's a case where we can do one step of a Gröbner degeneration and preserve the Cohen Macaulay property. It's also obviously not the case that if my variety is Cohen Macaulay, then all of its components are. But here is a case where we do get to say, here's my variety that's Cohen Macaulay, and also its component is. So getting to pass the Cohen Macaulay property through these partial Gröbner degenerations that maybe aren't in a setting that's as nice as the Conca-Barbaro setting is something that that I'm very interested in working towards. So with the setting as it is, what do we know and what do we not know about diagonal Gröbner degenerations of matrix Schubert varieties? So one thing that we do not know is we don't know a diagonal Gröbner basis for Schubert determinantal ideals, even if they're radical. There's a case that is classified by pattern avoidance, and which gets you, I mean, it's broader than the Wechsler case, broader than the Banner case. It's called CDG after Conca, Denegri, and Gorla. But that was originally conjectured by Hamaker, Pechenik, and Weigandt. But it's a pattern avoidance result, so that means it's 0% of Schubert determinantal ideals. So it would be great if we could understand a positive percentage of Schubert determinantal ideals and know their Gröbner bases. One thing that's interesting here is, so in the radical case, we know exactly what the initial ideal is. So if you could guess the Gröbner basis, and you could guess, then you can check immediately whether or not your guess is right. In the case where the initial ideal is not radical, if you had a guess, you couldn't check it immediately. And the reason why you couldn't check it immediately is because we only describe the components, so the things that are the same dimension. We don't describe embedded primes. So there are some initial ideals of Schubert determinantal ideals that have embedded primes. We don't know what they are. Anna expects that it's also governed by pattern avoidance. I have literally no intuition on it. But there are some. So in those cases, we don't, if you had a guess, you couldn't check it immediately. We also don't know, suppose that it's like the example that we did, where we had no embedded components, but we did have some multiplicity in the minimal primes. We don't have a clear description of all of the ways that the multiplicities can or can't manifest. Meaning we don't necessarily know which of the variables is squared. That I do have a guess on, but I have no way to prove it. No ideas. Another thing that we don't know is what the Gröbner fan looks like. So we don't know if there are other Gröbner degenerations that give us other ways to study double Schubert polynomials. So specializing a double Schubert polynomial, then to recover a single Schubert polynomial and to be able to study these structure constants in polynomial ring mod ideal generated by the elementary symmetric polynomials. So we don't have, so maybe if we got a better understanding of other Gröbner degenerations, we would be able to understand Schubert polynomials and double Schubert polynomials better, and then make some leverage on this ring that we decided, half an hour ago was really fun. And we also don't know, aside from Gröbner degeneration, are there other ways of understanding double Schuberts or Schuberts that would otherwise feel algebra geometrically natural to us? There are a lot of combinatorial formulas, and to the best of my knowledge, a lot of them don't have any algebra to go with them. In the Cohen Macaulay setting, there is so we know from Fulton that, and then I guess again from Knutson and Miller, that all matrix Schubert varieties are Cohen Macaulay, but we don't know when their intersections are. I apologize, we don't know when their unions are, intersections of the ideals. So in particular, we don't know when alternating sign matrices are Cohen Macaulay. So even if we restrict to equidimensional alternating sign matrix varieties, some of them are Cohen Macaulay and some of them are not, and we don't really have a foothold on when they are. When they are, we also don't know anything about the usual questions that we ask about Cohen Macaulay varieties. So we don't know anything about the resolutions, about the regularity. So a bunch of other homological algebra questions still open. So at this point, my pitch is that I think that we in commutative algebra should be studying matrix Schubert varieties and alternating sign matrices a lot. They have been our friends since the 70s through their connection to Schubert varieties. And also, we like ladder determinantal ideals, so we should like matrix Schubert varieties. And there's this really strong foundation of a lot of combinatorics and geometry there, and there's a lot of work to do for commutative algebraists. So the questions that we usually ask about Cohen-Macaulay varieties are essentially untouched. So there is a lot of fertile ground, and in my experience, it's really fun. So I will end there.
Excellent. Let's thank Patricia. Are there any questions?
I have a question.
Go ahead.
Go first.
Okay, so can you like go back in the slides when you show the example with the multiplicity?
Yeah.
Let's see. Right. So I was scribbling. So the initial for IW2 shouldn't just be Z11 times Z22, right?
Yes.
So how comes that when you intersect Z11 with Z11 times Z22, you get Z11 squared?
So you're not taking the initial ideals and then intersecting?
Oh.
You're intersecting and then taking the initial ideal.
Okay.
So so you take Z11, Z22 minus Z21, Z12. And the first thing you do is you multiply that by Z11. And then after that, you take the initial ideal. So you're taking the initial ideal of the polynomial that is Z11 squared times Z22 minus Z11, Z12, Z21. Good question.
Order operation makes sense now.
Becca.
Oh, I wanted to ask, so you had the really interesting setup at the beginning where you had death rays, and I think I missed how that connected to the Bumpless pipe dreams. Would you be willing to, is it just that they get the same variety or something?
So the, so we can, if we take the dots and we smooth them out into elbows, and we just sort of get rid of the numbers, then we'll have what's called the Bumpless pipe dream for this permutation. So it's the Bumpless pipe dream that sees all of the other ones, because one, due to Shimozono, one way we can define Bumpless pipe dreams if we want, is start from the Bumpless pipe dream that is this diagram with the death rays, but with the corners turned into elbows, and then perform whatever sequence of droop moves that you want. So I could say droop this, it would in that case be a pipe, down into say this square or into that square. And so the this is called the rota diagram. The rota diagram is the same information as the Bumpless pipe dream, and then it's droops of the Bumpless pipe dream that give you all of the Bumpless pipe dreams.
Thank you.
I appreciate all of your patience with the many combinatorial objects and the different types of squiggles, some of which are the same and some of which are not. I know it's not it's not something that's often asked of me at your talks, and I would find it difficult to track all of the information.
I mean, Cohen Macaulay, you drew pictures to represent it, and Bumpless pipe dreams. I mean, great words. So am I correct? So you said sort of the things that you would study for a given Cohen Macaulay thing, there's fertile ground there. So do I hear that, like the computation of the canonical modules?
Yeah.
For instance, do you know what can you read the type, the Cohen Macaulay type, at least?
No, so like when our matrix Schubert varieties Gorenstein is, to the best of my knowledge, not known. When our Schubert varieties Gorenstein is understood by pattern avoidance due to Wu and Yang. But you can get from a statement of all Schubert varieties to all matrix Schubert varieties, but if there's a way to get from some Schubert varieties to some matrix Schubert varieties, I've never heard this described as a standard tool. Yeah, so that's my knowledge. We don't even know we know no results on, I mean, except for kind of trivial ones where like if all I have are zeros, then like obviously it's Gorenstein. But I don't know of anything that's been worth writing down.
Okay.
So certainly nothing more broad about Cohen Macaulay type.
Thank you. Last call for questions. All right, let's thank Tricia again.